Thank you very much, Gunter. So, well, I'm pleased to be speaking to this crowd. And so I have the luxury of 3 lectures to talk about a subject that's really actually has its origins in the very first year of MSRI, back in 1983. The first paper in this subject was written by Gerardo Mendoza and Richard Melrose. And it's come into be quite a large subject. A number of people here are experts, far more expert than me in many ways, on many of these things. And but what I want to do over these 3 lectures is it's a different way of thinking about microlocal problems. In fact, I think it would be fair to say that geometric microlocal analysis is like, you know, that old saying about the Holy Roman Empire. You know, it was neither holy nor Roman nor an empire. So it's kind of like that. It's neither geometric nor analytic nor, you know, microlocal. But so it's a way of thinking about things, and actually it's a very good methodology for tailoring analytic techniques to geometric problems. Now, as you all know in PDE, there's this great interplay between geometry and analysis. And so like all this talk of Hamiltonian vector fields, and you know, there's this deep intertwining between dynamics and geometry and the underlying analysis. And this is another type of relationship, if you like. So today, so the plan for these 3 lectures is roughly the following. So today is going to be, sorry, I hate this hard big chalk. Let me see, if I use this small chalk, tell me if this is legible. And if not, I'll go back to the big chalk. So today, I'd like to talk about some generalities plus a case study. On my lecture tomorrow, I'd like to talk about some the technicalities of what makes this case study really work. So let's just say the nuts and bolts for this, you know, for this example. And then in my 3rd lecture, I'd like to talk about sort of the great variety of things to which this can be applied. So there are many, many different analytic and geometric scenarios, and I'll give you a little bit of a hint of it when I talk about these generalities. But I want to talk about some of these more general scenarios. So this is more examples. Well, I'll just leave it at that. Okay, so that's where I'm headed over these 3 lectures. And I think it's best to sort of start with I've been reading this wonderful book about aphorisms, so I'm going to give you 3 aphorisms to sort of keep in mind during this whole thing. Okay, so aphorism number 1 is, you know, when in doubt, compactify. Okay, aphorism number 2 is, if you're still in doubt, blow something up. I'll explain what this all means mathematically. And then the 3rd one is that smoothness is not what it seems. Okay, so you can think of today as sort of an explanation about why these are very reasonable aphorisms. Okay, so roughly speaking, our goal is to look at various classes of PDE. So we want to look at PDE and maybe generally pseudo-differential operators on spaces which are, well, non-compact or singular or degenerating. Now notice I said spaces rather than talking about operators. And in some sense, that's to be my emphasis. So as I said, there's sort of this nice interchange between geometry and analysis. So I'm really interested in operators that arise in specific geometric scenarios. Now, you can talk about a certain type of non-compact space, like Rn or hyperbolic space or something like that. You look at the Laplacian or some geometrically natural operator on it. It exhibits a certain sort of behavior. And then you invent a set of techniques that are tailored to that geometry, and then they work for many other operators, even if they're not of geometric origin, which have that same sort of structure. So roughly speaking, the operators which arise here have a singular or degenerate structure, or they might be nice operators, but they come in families where they start, you know, becoming terrible in the limit. So we'll see examples on each of these, but I sort of always introduce each of these operators in terms of the geometry of the underlying space. Now, for me, that gives an intuition, but you may sort of think differently. Okay, so when I talk about non-compact spaces, so examples of things I'll talk about are, for example, complete manifolds with nice geometry at infinity, with let's say a tame geometry at infinity. That's a little bit of a vague term, but I'll explain that later on. So examples are, well, Rn, Hn, higher rank symmetric spaces, locally symmetric spaces, various classes of Einstein metrics, various classes of interesting geometries that come up in special holonomy, and so on. So there are many, many spaces that arise in geometry that are not just sort of arbitrary out at infinity. So these might be spaces with good curvature properties, like I say, Einstein metrics or so on. And there are interesting hard analytic theorems which say that they behave very regularly at infinity. Okay, so this is what I have in mind here. Singular spaces, well, the simplest ones that one can think of are cones, edges, etc. And slightly more generally, these are contained within a class of things which I'll call stratified spaces. And one of the great successes of stratified spaces, one of the great successes of the whole business is that trying to understand analysis on these general stratified spaces is something that we've been thinking about for really a long time. And I'd say within the past 3, 4, 5 years, it's really come to a sort of a good state of fruition due to the efforts of a number of people in this room. And then finally, degenerating spaces. Well, so again, I'll give some various examples, but there are things that arise naturally in mathematical physics problems and geometry problems, adiabatic limits, neck stretching, and what I'll call geometric gluing. So these are all families of elliptic operators that have a parameter in them, and the unifying feature is that as that parameter goes to 0 or infinity, the problem becomes more and more degenerate. And I want to sort of find some good uniform way of treating these things. Okay, so again, that's very rough overview of what's going on. You might ask, why are we so interested in doing analysis on singular spaces, for example? Hopefully it's not so shocking that we'd want to do analysis on non-compact spaces. They're all around us. We've just been talking about, well, Maciek will be talking about scattering on our Rn and scattering manifolds later on. That's a particular case of this. Singular spaces, my philosophy has become more and more as I get older that, we're very, geometric analysts, we're very stuck on doing analysis on compact manifolds or maybe manifolds with boundary. But singular spaces are really just as a natural of a setting. And so, I can name many classes of interesting singular spaces that you're sort of forced into even when you don't mean to be when you're doing analysis on smooth compact manifolds. So, for example, level sets of Morse functions. Well, a generic level set of a Morse function is, of course, regular, but you're past these critical values where the level set becomes something like a cone or some sort of stratified set. There are compactifications of moduli spaces. Well, actually, even more primitive, well, a very complicated set, but let's say more classical, algebraic varieties. So there's obviously a very long tradition of trying to do analysis on algebraic varieties, compactifications of moduli spaces. So I'm not going to have a chance to talk about these except for in my third lecture. I'll try to give some examples where the types of operators I come up with are appearing, compactifications of moduli spaces, and finally compactifications of locally symmetric spaces. Okay, so if you're not a geometer, and you just want to look at PDE, I'll write down, in most of these cases, what the corresponding PDE look like. Now, when I talk about PDE, I'm mostly in these lectures will be talking about elliptic problems, Laplace-type operators, for example, or Dirac-type operators. I'll talk about parabolic operators to some extent, heat operators and related things. And there is some work in this world on hyperbolic operators, wave equations, and so on in these singular spaces. And I won't be talking about those out of the interest of time, but there already is some very, very interesting work in that regard. Okay, so we'll focus, certainly today, we'll focus on elliptic operators. And so what you saw this morning and this afternoon was the whole, well, we have two ways of looking at elliptic operators. So I'll start with the general nth order elliptic operator for the time being. So this may look like this, A alpha of D, dz to the alpha, mod alpha less than or equal to m. So this is an nth order differential operator. I'll always be assuming that I have smooth coefficients. There is a certain amount you can do in this theory with non-smooth coefficients, but let's assume that these coefficients are C infinity. Ellipticity, of course, means that this principal symbol, sigma m of L, z zeta, which is equal to the sum mod alpha equals m, alpha of z times zeta to the alpha. This is invertible. So, this is a scalar operator as I've written it, but equally well I could be looking at L as an operator system. So this could be acting between sections of two different vector bundles. This is a local coordinate expression for it, and this would be a zeta dependent. This is a parameterized family of matrices, and I demand that those be invertible when zeta is not equal to 0. So I've taken the principal part. Okay, so that's the principal symbol of this operator. So we're going to be looking at elliptic operators. And we have two distinct points of view when trying to do things with elliptic operators. So on the one hand, we have a priori estimates. So that might be that, for example, in Sobolev norms, so U in the HS plus M norm is bounded by some constant times L of U in the HS norm, plus, let's say, U in, well, as Andras said, in the minus N norm, let's suppose that S and M are positive, so in the 0 norm, the L2 norm. Okay? So this is a classical a priori elliptic estimate. And, there's a local version or a global version if I'm on a compact manifold. And then the other point of view is a parametrics. So a parametrics is a pseudodifferential operator G. So this is going to be a pseudodifferential operator of order minus M. And let's suppose for the moment that I'm on a compact manifold. So there's no boundary, there's no infinities to worry about. This is just, sort of a local theory, but pasted together finitely many times. Parametrics G is an operator that satisfies L of G is equal to the identity minus R1. G of L is equal to the identity minus R2. Here, so I've said G is in psi minus M. R1 and R2 are smoothing operators, so they're pseudodifferential operators of order minus infinity. Okay, and out of this one in particular, so suppose that L of U equals F, I apply G to both sides. I'm going to get U minus R1 of U, that comes from applying G to the left-hand side, is equal to G of F. Okay, and then if I just apply the boundedness property, so here I've just said the existence of a parametrics, but then I need to know that it's bounded between certain Sobolev spaces, for example. What I'll get is that the HS plus M norm of U is bounded by a constant times the HS norm of F. That's using the boundedness of this guy, HS, plus the L2 norm of U. Right? So what am I actually using here? So this uses just the fact that G is a mapping from HS to HS plus M is bounded. And this R1 I have is bounded from any HT to any HT primed for all T and T primed. So it's a smoothing operator. Okay, so these are two different points of view. From these, you get various functional analytic consequences. So if you're on a compact manifold, then these operators R are compact. Right? Compact operators in L2 or in HS, and you get that U is the L is a Fredholm operator. And then the minute you have Fredholmness, then you can deduce various nice things. So for example, the Hodge theorem, one of my favorite theorems, is like just a two-line proof once you know Fredholmness in closed range. Right? So the minute you have a parametrics, then you can deduce a whole raft of very nice consequences. So I view that this is sort of the the primary goal, if you like, and really, I wanted to emphasize the point that geometers get too hung up on a priori estimates just because they read Gilbert and Schrödinger. But if you read Hermander or somewhere else, you know that parametrices are a very flexible tool and equivalent. So really, there's not much to be gained going from one to the other, except for that these are kind of more geometric objects. Okay, so I'll try to justify all of that. Okay, so now here's maybe a better better title for this series of lectures, which is a global theory of parametrices. And so I'd say really the point is that if you're talking about an operator L on some space, I'll call M, so this is a manifold, but there I had it just as a smooth compact manifold. This thing could be more general. It could be an open manifold, it could be a singular space, something like that. If I have an elliptic operator in this manifold M, I construct a parametrics for it. Okay, now I've talked about this parametrics being a operator, right? So it looks like a, forgive me. So this thing I've talked about as an operator. I'm going to very quickly now shift to it as a Schwartz kernel. So I want to identify the operator with its Schwartz kernel. This Schwartz kernel is a distribution on M cross M. And the whole point is it's the geometric structure of this distribution, which is important. So we care about the geometric structure of this distribution. And in fact, that's really the whole story, is that we're really very interested in finding the global geometric structure of a parametrics or a generalized inverse for an elliptic operator. That contains an awful lot of information. The geometric structure contains various things. So remember, here's M cross M. So here it is. There's M, there's M. And we already been learning this morning that, the big action, or so to speak, is along the diagonal. So we're expecting to have this pseudo-differential singularity along the diagonal. This is a smooth function away from the diagonal. But if M has boundary or corners, well, I'm compactified a little bit. I'll explain that picture a little bit more. There's a lot of interesting stuff happening out near the boundaries a long ways from the diagonal. So that's really the moral, that the very far off diagonal behavior is really important. Okay? So that's where we're headed. Now, historically, I just want to say a few words about all of this. So if you go back into the prehistory of this subject, so back in the 50s, there was this great development of singular integral operators. And that was really all about Schwartz kernels. Of course, they didn't call them that in those days necessarily, though the Schwartz kernel theorem had been proved. But singular integral operators were a special class of convolution operators on Rn, and there was extensive development of what spaces they were bounded on and so on. But it was really a focus on the precise regularity properties of the Schwartz kernel. So this would look like some homogeneous function x over z over mod z divided by mod z to the n, where let's say the integral of f is equal to 0 over Sn minus 1. Okay, and you think of this as a convolution operator. Okay, so there's a lot of work on this. This led in the late 50s and early 60s, so people tried to understand. So Bob Seeley's thesis was about showing some sort of coordinate invariance of these things. They existed on manifolds, and the flexibility of the coordinate invariance led to a huge number of advances. I mean, the Atiyah-Singer index theorem was one of the primary goals at that point. And from that, as you all know, this led to the various formulations of pseudo-differential operators. So let me just say the oscillatory integral representations of pseudo-differential operators, for example. And the calculus of pseudo-differential operators developed in the early 60s. And then it was this paper in the early 80s. So this is now early 80s. And so this is really the work of Richard Melrose and his various collaborators, which led back to this sort of geometric theory of taking the Schwartz kernels of these things seriously. Not so important if you're on a smooth compact manifold, but very important if you're on a more general manifold. So take the Schwartz kernel seriously. Okay, well, so. Okay, so I'd like to now move to a very classical construction about Schwartz kernels back in this setting, and it really parallels something that Xu En did this morning, but in slightly more geometric language. And then I want to move to an interesting non-compact setting. Okay, so what I want to talk about is the Hadamard parametrics construction. So I'll just review this briefly. So this goes back to Hadamard in, I don't know, the 20s or 30s. He originally did it, well, I mean, it works for elliptic, parabolic, and hyperbolic operators, both. He did it for the wave operator. Mike Taylor's book certainly has a nice version of this in volume 1. Friedlander's book on the wave equation on curved spacetimes is a very nice wave equation proof of this. I mean, you can find it in many, many places. So, let's start with this L. This is my elliptic operator. And what I want to do is I want to find a parametrics, G, and it's going to be given as an asymptotic series, Gj. J goes from 0 to infinity. So even though I'm sure it was talked about this morning, I'll remind you what that asymptotic series looks like. And the Gj's are, now this is going to be on the level of Schwartz kernels rather than on the level of oscillatory integrals. So I'll be doing this on the other side of the Fourier transform. So G naught is going to be my first approximation. L G naught is equal to the identity minus R naught. So what I'm trying to do is solve this as best I can. Now, the thing that you try to do is say, well, suppose we were in the most easy situation, which was L just looked like its principal part. So here's a special case, which is not the exact case. So L just looks like its principal part. So I'm going to have this A alpha, and I'm going to freeze that coefficient. So this is dz alpha. So this is really an operator on Rn. Okay, so I'm looking at a constant coefficient operator, which is homogeneous. And I want to say, can I solve this problem here? Well, the answer is sure. I use Fourier transforms, but that's the only time I'm going to use Fourier transforms. So I use Fourier transforms, and I'm going to see, and this is very much like what Andras talked about in Schwen, I look at this G0. This is going to be an operator of z and z tilde. So I'm integrating, so this is an integral kernel. I integrate f of z tilde, g naught of z tilde, time, dz tilde. Right? This is going to be the inverse Fourier transform of 1 over this thing. So 1 over mod alpha is equal to m a alpha of z naught dz alpha. Okay? Now, there are various problems doing this. Obviously, if this is too singular, then this is not a locally integrable thing, and I don't know how to make sense of it a priori as a distribution. So sometimes you have to make choices. So I'm going to finesse those, but remind you of the situation, for example, with the Laplacian in Rn, where m is 2. This looks like inverting 1 over xc squared. That's a L1 loc function, and it's tempered at infinity, and there's no problem of taking the inverse Fourier transform in the world of temperate distributions. And in fact, this is better than just an arbitrary temperate distribution. It's a homogeneous distribution. So this thing is a, oh, excuse me, I screwed up here. Somebody should have yelled earlier. Sorry, this should be a zeta to the alpha. So I've taken the symbol of this. I've taken the principal symbol, inverted it, and taken the inverse Fourier transform. So forgive me. Okay, so that's G naught. So, strictly speaking, this is e to the I z minus z tilde dot zeta, and then times this 1 over mod alpha equals m a alpha of z naught times zeta to the alpha d zeta. And of course, what I might do is cut it off. So this is the cutoff function, which is 1 near infinity and cuts away the singularity at 0, for example. So that that will sort of be a good way to heal what's happening if m is large, much bigger than the dimension, for example. But in any case, if I didn't do this, I have a homogeneous function, which I can interpret it. If it's an L1 log function, it's a distribution. Its inverse Fourier transform is, again, a homogeneous distribution. And we all know what this is. In the case when m is equal to 2 and L is equal to the Laplacian, this leads to the inverse Fourier transform of 1 over mod zeta squared is up to a constant. It's 1 over mod z to the n minus 2. So this is just some sort of generalization of that. Okay, and to put in my same language here, it's 1 over z minus z tilde to the n minus 2. And there's some dimensional constant, which I'll omit. Okay? Okay, so G naught is going to be given by this. But so the way you should be thinking about this is that at every point there's a model. It's a constant coefficient model, and we have to invert that. Now, this inversion is not a particularly big step. We just use the Fourier transform, but we have to invert the model operator. Now, why I'm stressing that is if we have a more complicated space with singularities and strata at infinity and so on, you're going to have a model at every single place at infinity, and you're going to have to invert all of those models. That's the serious work to be done. And the variable coefficientness of the operator is actually just going to be buried in these sort of infinite series of correction terms. So, the serious analysis, which is not very serious here, is just inverting the model. Okay? Okay, so what do I get if I do this? So if I take L of G naught. So I'm going to get the identity operator, but I'm going to have made a bunch of different error terms. Now, first of all, notice that I did this at a given z naught. So in fact, what should I really be doing? Here I am on m cross m. I take a given point z, right? There's z. I want to then exponentiate. I want to look at a local coordinate system based at z. Okay, so z tilde, so I'm thinking about z tilde is equal to z plus some w. So I'm thinking z as being like the origin, and then w is sort of added on. If on a manifold, I want to sort of exponentiate out with respect to any fixed Riemannian metric, for example. So I'm just sort of taking a neighborhood here, which I'm parameterizing by a neighborhood of the zero section in the tangent bundle, for example, right? And I'm sort of doing this at every point. So I've solved this local model. I'm at every single point of my manifold, and then I string those all together, and what do I get? Okay, so what I get is an error term, so L of G naught. So it's going to look like the identity plus some error term. And roughly speaking, the error term is going to have things in it like this. So this is going to include, for example, e to the I z minus e tilde times zeta. Now I'm going to have this 1 over, so mod alpha is equal to m of a alpha of z, zeta to the alpha. And up here, I'm going to have all the subleading parts. Mod alpha less than m, a alpha of z, zeta to the alpha, right? So the identity was when I took the leading part. I just have the Fourier transform, inverse Fourier transform, but I have all the subleading parts here. And then I'm going to get plus a bunch of junk terms that come from the cutoff errors. I've fixed, you know, this exponential map. I mean, there's all sorts of junk terms that come about. Those all get glommed into here, okay? So at the end of the day, I have this identity plus an error term. This thing is clearly better because this is a polynomial that is of order m minus 1 or worse or better, divided by something exactly of order m. The inverse Fourier transform, well, that's something decaying at infinity, so its inverse Fourier transform is a little bit smooth. Okay? So let me encapsulate what we get. G naught of z and z tilde, and this is what you just get by some generalization of this argument or understanding the theory of Fourier transforms of homogeneous distributions. This thing looks like some, well, let's say, roughly speaking, it looks like something, so it might look, let me see, so it might look like an a0 of z times actually it probably looks like an a0 of, well, just say z, times the distance between z and z tilde to the power m minus n. Maybe it's a little bit more complicated than that, but roughly speaking, it looks like that. Okay? So it looks like a generalization of the Newtonian potential. When m is equal to 2, that's 1. That's just the Newtonian potential. This is some variable coefficient version of that. What this R naught looks like, if I take L of G naught is equal to the identity minus R naught of z and z tilde, this R naught has a Schwartz kernel that looks like, well, it's a little bit better than, well, the identity looks like essentially distance of z minus z tilde to the minus n, right? That's something of order 0, so it's going to look like that. So this will look like something of order distance from z to z tilde of the order 1 minus n. So this is a locally integrable, this is a locally integrable thing. It's a little bit smoother than the identity operator. Okay, you've gained a little bit. Okay, well, you keep on going. So that's what all the higher g's are, is you just keep on adding correction terms. So I'm going to add on g naught plus g1. This g1 is going to be one order smoother than this g naught, so it's going to have a distance to the m minus n plus 1, and I'm going to get an error term that's of order 2 minus n, distance to the 2 minus n, and so on. So I'm going to keep on adding these things. So if I add some finite sum, I'm going to have identity minus r sub n, and this r sub n, now here's what's a little bit confusing. R sub n is going to look like distance from z and z tilde. So what should it be? It should be minus n plus 1. I think I'm about right there, hopefully. Right? But then there might be a C infinity error. So this comes about from all these junk terms and these sort of exponentials and so on, the cutoff functions and commutators with cutoff functions and so on. So I get an error term which is better and better behaved in terms of the distance function, but then at some point it gets swamped by just a general smooth term. Okay? Now, I'll explain why that's not so important as we go along. So we'd hope to get an error term which is really going to 0 in some sense asymptotically. But there's this sort of obstacle that keeps on sort of blocking it from being 0. Okay, now next sum is we take an asymptotic sum. So I find a G which looks like, maybe I call it G tilde, which looks like the sum of these GJs. So what I'm looking for, so this is a version of Borel's lemma, which was surely discussed this morning. Namely, you try to find a function that is, well, not quite smooth, but it has this asymptotic development where if I take any finite sum of these guys, take G tilde minus any finite sum, it decays like the next one. Okay? And what I'm going to get is that L of G tilde is equal to the identity minus an R tilde. And this R tilde has now 2 bits, a piece which vanishes to infinite order on the diagonal, plus a general smooth term. So I can just say R tilde is just C infinity of M cross M. It doesn't make sense to keep track of this. But the reason I kept track of this at each stage is, of course, this thing may not be perfectly regular. If minus n plus capital N plus 1 is odd, right, that's not a smooth function. Right? So I want to keep track of these and subtract off any possible singularity that comes on the diagonal. Right? But I always have this sort of smooth bit which is swamping it. Okay, so this is the Hadamard parametrics construction. As I said, there's a similar version for heat operators and wave operators. And the minute you have this, you have to understand, is G tilde bounded on Sobolev spaces or Holder spaces or Treble-Zorkin spaces or whatever you like? Right? So is this G tilde bounded? But the minute you know that, then you're kind of done. You get these a priori estimates. You can prove whatever nice geometric theorem you want. This is kind of the key. Okay, so this works on any manifold. The difference is that R tilde is smooth, and if you're not on a compact smooth manifold, this R tilde will not be a compact operator. So let me state that clearly, because that's an important issue. So this always works, by which I mean on any M. But if M is open or singular, then this error term, R tilde, which is in C infinity of M cross M, is not necessarily a smoothing, a compact operator. So why do I care about compactness? Well, just the usual proof, which I always teach in my first year functional analysis course. Suppose I take the transpose of this. So I'm going to get G tilde L is equal to the identity minus R tilde, transpose, whatever, blah, blah, blah. I have the transposes of these operators. If this thing is smooth, R tilde transpose will map, well, distributions of any order, let's say compactly supported distributions of any order, E primed of M, into C infinity of M. But it doesn't regulate growth at all. Now, if I'm a little bit more careful with growth, like suppose, for example, that here's the diagonal, and I just cut everything off to be supported in a distance 1 neighborhood of the diagonal, then with a little bit of work and a few minor assumptions, you can assume that whatever the rate of growth of this is at infinity, this smooth function has the same rate of growth. But it does not improve growth. It doesn't make you decay faster. This is not a compact operator in general. So the only time it's a compact operator for sure is when you're in a compact manifold. And remember, the compact operator is just something which is morally 0. Right? It's something that you can functional analytically get rid of except for a compact, except for a finite rank error. Okay, so forgive me, that's a very classical thing, but it's worth seeing again because now we generalize that. Okay, so what we're going to talk about is the corresponding situation in a progressively more general set of circumstances. So I first want to start with hyperbolic space, Hn. Okay, now I'm going to take all of the aphorisms that started at the beginning and I'll progressively apply them. Okay, so hyperbolic space is, well, either you love it or you don't love it. I happen to love it. But, there you go. It's a nice source of degenerate elliptic operators. And the minute I write out what this operator is, now guarantee that even if you only like smooth non-degenerate operators, you're still actually in this setting, in a sense I'll explain before. Okay, so Hn is, well, there are three models for it. The upper half space model, or the Poincare disk, or the Klein disk. Well, there are a few other models too, but these are the ones I'm going to consider. Okay? And the upper half space model, so what I'm going to do is write down the Riemannian metric in each case, and then I'm going to write down the Laplacian, and the Laplacian is going to be rather degenerate. So if you try to treat this by standard old-fashioned, a priori estimates, you're not going to get very far. You'll get a little distance, but you're not going to get very far. Okay? So this parametrics method has to be improved. What I did was I used this normal operator, this model operator everywhere along the diagonal. I'm going to have different model operators at infinity. Okay, so here the hyperbolic metric. So this is just to drive the complex analysts here crazy. I let x be the vertical coordinate. So here it is, dx squared plus dy squared over x squared. This y is an Rn minus 1. The Poincare disk, my coordinate in here is z. It's going to be 4 dz squared over 1 minus mod z squared squared. And then this guy, let me see if I get the formula right, it's 4 times the sum of zj dzj squared over 1 minus mod z squared squared plus, I think it's a 4 times dz squared over 1 minus mod z squared. Now, obviously, in terms of simplicity, this is the simplest. This is a little bit worse, but not too bad, and this looks horrible. Right? However, they all have their nice advantages. And so this space, it exhibits a certain symmetry of hyperbolic space. There's a clear translational symmetry. If I translate, this metric stays the same. I can also dilate. Notice I have homogeneity 2 on top and below. So if I dilate coordinates, lambda xy goes to lambda x lambda y, that's an isometry. It preserves this metric, and so that says that natural operators should be invariant under this. This exhibits a slightly different symmetry, rotational symmetry, which looks kind of awkward in these coordinates. And this, you can see the rotational symmetry too, but, well, this has the property that geodesics are straight lines. Here, the geodesics are circular arcs, which are perpendicular to the boundary. Okay? Now, already implicitly, remember my first aphorism, when in doubt, compactify? So I've already compactified, in a sense, by sort of implicitly putting this boundary here. Hyperbolic space is the interior. The metric blows up as I get to infinity. The metric does not exist here. So it really is sort of this complete space in here that I'm interested in. But I've added on, well, here a piece of the boundary. Here I've added on the entire boundary. Infinity in this picture is some point here. Similarly, some point here. So I've compactified. Now, why do I do that? Because we're going to be analyzing off-diagonal behavior of the green function, of the parametrics for the Laplacian, for example, and we want to see exactly what it looks like at infinity. So that's where we're headed. Okay, so I can write down the Laplacian, and again, it's going to look nicest in these coordinates. So I'm going to write down the Laplace-Beltrami operator. So in that last thing, it's going to look like x to the n d by dx of x to the 2 minus n d by dx plus x squared times Laplacian in the y variables. And I'm going to not settle on which sign of the Laplacian I want with pluses or minus signs. I'm going to flop back and forth, and it's your job to figure out where I'm at any given moment, okay? Okay, so this looks like x squared d by dx squared plus 2 minus n x dx plus x squared times Laplacian y. Okay? So that's a degenerate operator. If I'm treating this when x is positive up here, nice, easy elliptic operator. All the pseudo-differential stuff this morning works fine. But what you do is you get near the boundary. Okay? Now, as I said, even if you don't care at all about geometry or hyperbolic space, you should care about operators of this type for the following stupid reason. Suppose you have the Laplacian, dx squared plus dy squared, or let's say a more general mth order operator, a alpha of x and y, dx alpha beta, no, excuse me, dx j alpha, dx to the j, dy to the alpha. So using multi-index notation, some general elliptic operator, right? Doesn't look much like this. This looks much nicer. But I can actually treat it on the same footing by multiplying by, if this is j plus mod alpha less than or equal to m, I can multiply by a power of the distance function to the boundary to put it in the setting. Now, this looks terrible, right? I've taken a nice, good operator, made it very degenerate. And I claim that actually this, well, you can view it two ways. Either that this sort of brings out sort of the inner homogeneities of this operator. And if you look at sort of classical derivations of elliptic estimates at a boundary, there are various mysterious things that go on. Now, they're very classical and you don't think of them as mysterious, but if you really think about it, they're a little bit unnatural. And I claim that when you look at them in the guise of hyperbolic geometry, they look very natural. So I don't know if I'll have time to talk about that, but in a certain sense, a lot of the phenomena that you see for boundary problems for non-degenerate elliptic operators look much more natural from the hyperbolic point of view. Okay, so that's just sort of a dictum. So that's why I'd want to do this. Now, I can also write down the Laplacian in one of these other coordinate systems. So, for example, one of these other guises. So, these all look different, but they're the same thing. There's a coordinate change, a diffeomorphism, which takes each model to every other and preserves the metric. Takes one metric to another. In the Poincare disk model, I'm going to have the following. So let me see if I can get this right. So I'm going to have 1 minus mod z squared to the minus n divided by, well, I'm going to forget about the 4s. I'm just going to get them right. dzi of 1 minus mod z squared to the 2 minus n. I only have diagonal bits. This is just a Euclidean metric, dzi, sum over I. So this looks like up to a factor of 4 or something. This is going to look like 1 minus mod z squared times Laplacian in the z variable, plus this sort of extra kind of funny thing. So I'm going to have 2 minus n times minus 2zi times 1 minus mod z squared. So I'm going to have to the 1 minus n and minus n, so that's just going to be to this power times dzi. Okay, so this looks, again, sort of fairly ghastly, but the important thing is that I now am on a smooth, so I've really compactified. I'm in a smooth compact manifolded boundary. Okay, and I see this operator, and this operator sort of partially in the following thing. So let me go back to this model here for a second. Here I have x and y. This operator up top is a combination of the vector fields x d by dx and x d by dy. So namely, I take a polynomial in those vector fields and I get that operator. What's important about these vector fields is that these are, if I take linear combinations of them, they're arbitrary smooth vector fields in the interior, but they vanish at the boundary. So that's sort of the underlying geometry here, that I take a manifolded boundary, I take arbitrary smooth vector fields in the interior, which vanish simply at the boundary, and I take elliptic combinations of them, and that's what these operators are. Okay, now I'm going to run through a series of parametric constructions, and let me tell you what the geometric settings I'm going to talk about are, because they're interesting geometrically. So the first one is hyperbolic space itself. And I'm going to write down the parametrics, and it's just like I wrote down the parametrics, an exact inverse of the Laplacian in Rn. Okay? The next one is, suppose I take a hyperbolic space and I remove a domain. So I take Hn minus some compact subdomain. Or slightly differently, I can take a compact perturbation. I can take a Laplacian plus a potential where v is in C infinity 0. Okay. Then the next case I want to talk about is one that may be geometrically unfamiliar to you, things that look like quotients of hyperbolic spaces, and I'll draw sort of a two-dimensional version of it. So these are things that look like hyperbolic space at infinity, but they can have a complicated topology. So these are so-called convex cocompact quotients. Okay? So the point is, this is a progressive, not quite microlocalization, but a progressive localization. I have the full-on hyperbolic space. I localize near infinity. And here I have things that just near in small neighborhoods look like hyperbolic space. And then the final generalization will be what I'll call MG conformally compact, which means that the metric G is, M is a manifold with boundary. G looks like rho to the minus 2G bar. So it looks like some kind of, abstract generalization of hyperbolic space in the Poincare model. I take a smooth metric up to the boundary of a compact manifold with boundary, and then I screw it up by dividing by the defining function squared. So rho is equal to 0 on the boundary of M. D rho is non-zero there. Okay, so this is a big Riemannian generalization of these various cases, right? This is kind of like the general variable coefficient operator of this type, roughly speaking. And these are things that are progressively worse and worse, so this is the simplest getting towards this. These cases have a lot of geometric interest. So for example, if these guys are Einstein metrics, which are conformally compact, this is a class of Poincare Einstein metrics, which are the basis of what's called the ADS-CFT correspondence in string theory. They're very interesting spaces with special curvature properties that a lot of people study. Okay, so let's talk about the inverse on hyperbolic space and then progressively move up the scales here. Okay, so on Hn itself, I have the fact that this space has a lot of symmetries. So on Hn cross Hn, if I have a z here and a z tilde here, right, that's where this g of z and z tilde should live. Okay, so I'm on Hn cross Hn. What I know is that given any 2 points, I can transform them to any other 2 points, provided the distance between those 2 points stays the same. So here's hyperbolic space, here's z and z tilde. Here's another point, w and w tilde. And as long as the distance between these guys is the same as the distance between these guys, then g of z and z tilde is going to be the same as g of w and w tilde. Namely, it only depends on the distance between the points. That's just because I have a space which is very rich in isometries. Okay, so I might as well put z tilde at the origin. Right? I put z tilde at the origin. And I can think of g as a function of z. Now I use the rotational symmetry. Right? This thing is any rotation around the origin is an isometry. So this should really only depend on absolute value of z. So in fact, I've reduced this to a function of one variable. Okay? Okay, so what I'm going to get now, I'm going to introduce yet another model for hyperbolic space. I'm going to use the geodesic polar coordinates. So I'm going to use spherical coordinates on Hn. R is distance to some fixed point. Let's say the origin, and then theta is a variable in the sphere. Here's yet another representation of the hyperbolic metric. dr squared plus hyperbolic sinh d theta squared. Okay, what that means is that the Laplacian is going to look like sinh to the 1 minus n of r, d by dr sinh n minus 1 r dr plus 1 over sinh squared d theta squared, Laplacian theta. Right? And if I expand this out, I'm going to get dr squared plus n minus 1 hyperbolic cosine over hyperbolic sine dr plus 1 over sinh squared r Laplacian theta. Okay? Now, here's this g. It really only depends on r. Well, mod z is going to be a function of r. Okay, so what I want to find out is, let me see, I don't want to erase this one yet. So I'm going to think of g as a function of r. Right? So g has to satisfy this. This part's gone because it's an ODE. So really, this g should satisfy g double primed plus n minus 1 cosh r over sinh r dr, g primed is equal to 0 when r positive. Okay? Really, what I want is that there's supposed to be a delta function at r equals 0 here, of course. Okay, so if I think about what this means on the positive real axis, so here's the r-axis, here's 0. What I'm looking for is the solution which is big at r equals 0. And if you just analyze this, and this is just an ODE problem now, so you have to go back and learn your ODEs again if you've forgotten them. But this is just a regular singular ODE problem. And solutions look like r to the 0 or r to the 2 minus n as r goes to 0. These are the so-called indicial roots of this operator if you go back and look at your regular singular theory. Okay? So these are just leading order terms of these things. Clearly, this is not the guy I want. This is the guy I want, r to the 2 minus n. So I'm looking for the solution that blows up like r to the 2 minus n. That's the, remember, r equals 0 corresponds to the diagonal. Okay? So near the diagonal, it's looking just like the Newtonian potential. But what happens as I go to infinity? To that solution? Well, this is a bit of a complicated ODE, so you have to work hard. And what you're going to find is that I'm going to use a new variable. I'm going to let e to the minus r, so I'm going to let rho be e to the minus r. Now, r is equal to distance. D is equal to the exponential, 1 over the exponential of the distance. Okay, so what I'm going to find is that g looks like rho to the n minus 1 as rho goes to 0, which is the same as r going to infinity. So I'm decaying like an exponential, a very fixed exponential in the distance function. Okay, now this is my third aphorism. So I could have taken the polar coordinate version, this just Riemann normal coordinates, and I took the radial compactification. So this is Hn, where I let 1 over r be a variable going to infinity. So 1 over r vanishes at infinity. This is just like, so Andras just mentioned this, didn't he? That, you take 1 over distance from the origin is a good compactification at infinity in Euclidean space. So I just take the geodesic, inverse here. That compactifies. I'm just sort of adding on the endpoint of any ray. And to say that something's smooth on this disk means what? It means that it's smooth in this function 1 over r. Okay? But now I've just told you that, in fact, this thing is behaving better with respect to a different variable. So in fact, I want to replace this by e to the minus r. And so in fact, what I've done is, now it's not a non-diffeomorphic smooth structure, but I'm introducing a different smooth structure on the ball. It happens to be exactly the one that appears in the Poincare model, but it's not the same as the geodesic compactification with respect to just this, r going to infinity. So I just say that the natural distance function to infinity is e to the minus distance. Okay? And what I found is that this Green's function, if it has a pole here, it decays like rho to the n minus 1 as I go to infinity. Now let's think what this looks like on Hn cross Hn. So I've compactified Hn cross Hn. I've compactified each hyperbolic space as a ball. I've done this compactification. The singularity along the diagonal is here, right? And what is this saying? Well, it's saying two things. One is that as I go towards here, this is r going to 0. It's blowing up r to the 2 minus n. As I go towards this boundary or this boundary, as I'm going a long ways away from the diagonal, right? What's happening? It looks like rho to the n minus 1. Okay, so I have an expansion here. In fact, there's an expansion in rho. It's a smooth function of rho starting with rho to the n minus 1 here and here. And along here, it looks like r to the 2 minus n. Have we understood things completely? Not quite, because there's these sort of funny regions where the diagonal hits the corner. So we have to understand those. And so here, we can do this. Now I'm going to sort of, remember, I'm going to use the upper half space coordinates again. Z is equal to xy, z tilde is equal to x tilde, y tilde. I'm going to draw a funny picture here. So here's the x coordinate, here's x tilde, here's y minus y tilde, and then there's y tilde sort of separately. And I'll explain why I do that in just a moment. And it turns out that this function, so I can write down I can actually write down what the function is. I'm not going to do it because it's a bit of a mess, but I can write it down, okay? Turns out that here's the diagonal here. This is x equals x tilde, y equals y tilde. So in these coordinates, this thing is equal to 0, and x equals x tilde. And I think of this y tilde as just some separate factor, which I'm not going to draw on the board, okay? And, well, remember I had this dilation invariance, which was a isometry of hyperbolic space, namely g of x, y, x tilde, y tilde is equal to g of lambda x, lambda y, lambda x tilde, lambda y tilde for all lambda greater than 0. Okay, if I just dilate out, it stays the same, because that's an isometry of hyperbolic space. What does that mean in terms of this picture? It means that this whole picture is dilation invariant as I dilate from this point. How do I picture dilation invariant things? Well, one way that's very effective is I introduce polar coordinates. Okay, so what I'm going to do is blow up this point. So I introduce spherical coordinates at the origin of this coordinate system, and I take them seriously. I put in the r equals 0 face. This is the polar coordinate variable distance at 0 face there, okay? So what I'm doing here, and this is kind of another aphorism which I could have written down, which is that I have some analytic complexity, is what's happening to this distribution as I get to this corner. And I'm going to trade it for geometric complexity. Here's a more complicated space but I have a simpler function. Okay? And so here's the basic theorem for the Laplacian and hyperbolic space. Its inverse, not just a parametric space, inverse is smooth on this space. Okay? Smooth in the sense that there's expansions as I go here, as I go here, as I go here. At the corners, it's like a product type expansion. And at these corners, higher codimension corners, it's a product type expansion. It's as smooth as you could possibly want. Okay? So that's the end goal. Now, that was exactly in hyperbolic space where I reduced everything to an ODE. Now, I just have a few minutes today, and tomorrow I'll sort of continue this discussion, but I want to talk about these various other cases. So let me talk. So how can I localize this discussion? So I used a lot of global properties here. How can I localize this discussion? Well, suppose I have Hn minus omega, or Laplacian plus v, where v is in C infinity 0. And this is compact inside of hyperbolic space. Okay? So the point is I want to localize this discussion near infinity. Okay? So I have hyperbolic space. I have some region in here where something bad is happening. Either I've emitted it with, let's say, Dirichlet conditions on the boundary, or I have a potential which is supported here. What do I do? Well, so the point is I'm going to choose G. Well, this is going to be a parametrics now, not the exact inverse. G is going to be, so I'm going to divide my domain into two regions. I'm going to let U1 be here and U2 be here. Okay? In fact, I'm going to have overlapping domains, so I take an open cover. And I'm going to choose functions. I'm going to choose chi1 and chi1 tilde in U1. So these are cutoff functions, chi2 and chi2 tilde in U2. And chi j tilde is equal to 1 on the support of chi j. Okay, so, for example, if chi j is equal to 1 here, then if that's the support of if that's the support of chi j, then chi j tilde is equal to 1 in a slightly bigger neighborhood. Okay? And I want to write G tilde is equal to chi1 tilde G in chi1 plus chi2 tilde G out chi2. Okay? So what I've done is I've created function just with the cutoff function. Now, remember, thinking of these as Schwartz kernels, so forgive me, I'll just finish this very quickly. If I'm thinking of these things as Schwartz kernels, I should put the z's and z tildes in. So this looks like chi j, well, chi1 of z, g in of z and z tilde times chi1 of z tilde, plus the corresponding thing for the out thing. Okay, so the right-hand guy is the z tilde, the incoming guy is the z. Okay. Now, what happens when I hit this with the Laplacian? Well, let's suppose I'm doing Laplacian plus potential. First of all, what is g in and g out? So g out is equal to, well, just this g hyperbolic. It's this thing which I've just constructed. It's the Green's function in a hyperbolic space. Okay? So what I'm doing is, near infinity, I just transport this global Green's function, but I cut it off. Okay? And g in, well, in the interior, I just have a smooth elliptic operator with variable coefficients, and I appeal to this morning's lectures, and I write down the parametrics for it. So this is a standard local psi dl, which is a parametrics for this. Okay? If I take Laplacian of this g tilde, so I'm going to have commutator terms and then the thing where this hits in the interior. So I'm going to have chi1 Laplacian g in chi1 plus chi2 tilde Laplacian g out chi2. And then I have commutator terms, Laplacian chi1 tilde g in chi1 plus Laplacian chi2 tilde g out chi2. This guy looks like identity plus some error term. This guy looks like the identity. I found an exact inverse at infinity. Okay? These guys, well, they're derivatives of these cutoff functions, so it's a mess, right? But what do I know about these things? These are, now I'm just using local pseudo-differential theory here, right? So these things are operators of order 1 applied to a pseudo-differential operator of order 2. Minus 2, I'm sorry. Okay? So altogether, you win 1. The composition is a pseudo-differential operator of order -1, and you win even more than you think because, why? The support of this guy is where chi1 tilde is changing. Chi1 tilde is changing precisely when, on the complement of the support of chi1. So if I were to draw, here's M cross M again. Here's the diagonal. Where is this operator supported? It's supported somewhere away from the diagonal, because wherever chi1 is non-zero, this guy is vanishing. Okay? So what I've done is I've created, and G interior and G exterior are smooth away from the diagonal. So these are sort of harmless terms because they're localizing away from the diagonal. Okay, so what I've done here is I've constructed the parametrics. And it's this principle that if I can construct a local parametrics near every bad point, well, the bad point here is all of infinity. So I have a local parametrics near infinity. I have a local parametrics at any point in the interior. I glue them together, and I get a global parametrics. Okay? It is smooth on exactly the same space. Its asymptotic structure is exactly the same. Okay? So I'll discuss that tomorrow, and then I'll talk about these other examples before going on to the real nuts and bolts of this theory. Yeah.
So some of the other non-compact examples you mentioned were like higher rank symmetric.
Yeah.
So what do you do when you can't sort of reduce your model to PDE?
Well, then you reduce it to a PDE that's simpler. So for example, if you take SL3 mod SO3, it's a rank 2 story, and you can reduce, the corresponding reduction to an OD here becomes a reduction to a PDE on a two-dimensional space, and it has a complicated structure at infinity, so it's a much harder problem. But you have to solve that model to understand, what's happening. Now, that's for the global story. And in some sense, what I'll be talking about tomorrow with these things is when I localize even further at infinity, I actually have to understand simpler models. Okay, so this was kind of a slightly bogus situation where I looked at the global hyperbolic setting as the universal model. It will be the universal model, but in a rather different way. So stay tuned. Yeah. Yeah. Oh, no. Precisely why I put it in. No, the reason I put in the Klein model was the following thing. So here I talked about changing the smooth structure at the boundary of the disk by sending R to rho related by these things. So things which are smooth in rho are kind of the good guys here, not smooth in R. Okay? The difference between the Klein model and the Poincare model, so in the Poincare model, things are smooth in rho. In the Klein model, things are smooth in the square root of rho. So there's this flexibility, and this is something that I think should be taken more seriously in geometric analysis. If you're in a manifold with boundary, the things that really matter are what's the distance function and any sort of fractional power of it. So that's actually the key there, is that if I replace rho by rho to the alpha for any alpha, that's kind of an equivalent structure in a certain sense.